By 330 BC, the Greeks had advanced their imperial reach into old Mesopotamia. This is Palmyra in central Syria, a once great city built by the Greeks. The mathematical expertise needed to build structures with such geometric perfection is impressive. Just like the Babylonians before them, the Greeks were passionate about mathematics.
The Greeks were clever colonists. They took the best from the civilizations they invaded to advance their own power and influence. But they were soon making contributions themselves. In my opinion, their greatest innovation was to do with a shift in the mind. What they initiated would influence humanity for centuries. They gave us the power of proof.
Somehow they decided that they had to have a deductive system for their mathematics. And the typical deductive system was to begin with certain axioms which you assume are true. It's as if you assume a certain theorem is true without proving it. And then using logical methods and very careful steps, from these axioms you prove theorems. And then from those theorems you prove more theorems. And it just snowballs that way.
Proof is what gives mathematics its strength. It's the power of proof, which means that the discoveries of the Greeks are as true today as they were 2,000 years ago. I needed to head west into the heart of the old Greek Empire to learn more. For me, Greek mathematics has always been heroic and romantic. I'm on my way to Samos, less than a mile from the Turkish coast. This place has become synonymous with the birth of Greek mathematics, and it's down to the legend of one man.
His name is Pythagoras. The legends that surround his life and work have contributed to the celebrity status he has gained over the last 2,000 years. He's credited, rightly or wrongly, with beginning the transformation from mathematics as a tool for accounting to the analytic subject we recognize today.
Pythagoras is a controversial figure. Because he left no mathematical writings, many have questioned whether he indeed solved any of the theorems attributed to him. He founded a school in Samos in the 6th century BC, but his teachings were considered suspect, and the Pythagoreans a bizarre sect.
There is good evidence that there were schools of Pythagoreans. They may have looked more like sects than what we associate with philosophical schools, because they didn't just share knowledge, they also shared a way of life. They may have been communal living, and they all seem to have been involved in the politics of their cities. One feature that makes them unusual in the ancient world is that they included women.
But Pythagoras is synonymous with understanding something that eluded the Egyptians and the Babylonians, the properties of right-angled triangles. What's known as Pythagoras' theorem states that if you take any right-angled triangle, build squares on all the sides, then the area of the largest square is equal to the sum of the squares on the two smaller sides.
It's at this point for me that mathematics is born, and a gulf opens up between the other sciences. And the proof is as simple as it is devastating in its implications.
Place 4 copies of the right-angled triangle on top of this surface. The square that you now see has sides equal to the hypotenuse of the triangle. By sliding these triangles around, we see how we can break the area of the large square up into the sum of two smaller squares, whose sides are given by the two short sides of the triangle. In other words, the square on the hypotenuse is equal to the sum of the squares on the other sides. Pythagoras' theorem. It illustrates one of the characteristic themes of Greek mathematics, the appeal to beautiful arguments in geometry rather than a reliance on number.
Pythagoras may have fallen out of favour,
and many of the discoveries accredited to him have been contested recently. But there's one mathematical theory that I'm loath to take away from him. It's to do with music and the discovery of the harmonic series.
The story goes that walking past a blacksmith one day, Pythagoras heard anvils being struck and noticed how the notes being produced sounded in perfect harmony. He believed that there must be some rational explanation to make sense of why the notes sounded so appealing. The answer was mathematics. Experimenting with a stringed instrument, Pythagoras discovered that the intervals between harmonious musical notes were always represented as whole number ratios. And here's how he might have constructed his theory.
First, play a note on the open string. Next, take half the length. The note almost sounds the same as the first note. In fact, it's an octave higher, but the relationship is so strong we give these notes the same name. Now, take a third the length. We get another note which sounds harmonious next to the first two. But take a length of string which is not in a whole number ratio, and all we get is dissonance.
According to legend, Pythagoras was so excited by this discovery that he concluded the whole universe was built from numbers. But he and his followers were in for a rather unsettling challenge to their worldview. And it came about as a result of the theorem which bears Pythagoras' name. Legend has it, one of his followers, a mathematician called Hippasus, set out to find the length of the diagonal for a right-angled triangle with two sides measuring 1 unit. Pythagoras' theorem implied that the length of the diagonal was a number whose square was 2. The Pythagoreans assumed that the answer would be a fraction. But when Hippasus tried to express it in this way, no matter how he tried, he couldn't capture it. Eventually, he realized his mistake. It was the assumption that the value was a fraction at all which was wrong. The value of the square root of 2 was the number that the Babylonians etched into the Yale tablet. However, they didn't recognize the special character of this number, but Hippasus did. It was an irrational number.
The discovery of this new number, and others like it, is akin to an explorer discovering a new continent, or a naturalist finding a new species. But these irrational numbers didn't fit the Pythagorean worldview. Later Greek commentators tell the story of how Pythagoras swore his sect to secrecy, but Hippasus let slip the discovery and was promptly drowned for his attempts to broadcast their research.
But these mathematical discoveries could not be easily suppressed. Schools of philosophy and science started to flourish all over Greece, building on these foundations. The most famous of these was the Academy. Plato founded this school in Athens in 387 BC. Although we think of him today as a philosopher, he was one of mathematics' most important patrons. Plato was enraptured by the Pythagorean worldview and considered mathematics the bedrock of knowledge.
Some people would say that Plato is possibly the most influential figure for our perception of Greek mathematics. He argued that mathematics is an important form of knowledge and does have a connection with reality. So by knowing mathematics, we'll know more about reality.
In his dialogue Timaeus, Plato proposes the thesis that geometry is the key to unlocking the secrets of the universe, a view still held by scientists today. Indeed, the importance Plato attached to geometry is encapsulated in the sign that was mounted above the Academy. Let no one ignorant of geometry enter here.
Plato proposed that the universe could be crystallized into 5 regular symmetrical shapes. These shapes, which we now call the Platonic solids, were composed of regular polygons assembled to create 3-dimensional symmetrical objects. The tetrahedron represented fire. The icosahedron, made from 20 triangles, represented water. The stable cube was earth. the 8-faced octahedron was air. And the 5th Platonic solid, the dodecahedron made out of 12 pentagons, was reserved for the shape which captured Plato's view of the universe. Plato's theory would have a seismic influence and continue to inspire mathematicians and astronomers for over 1,500 years. In addition to the breakthroughs made in the Academy, mathematical triumphs were also emerging from the edge of the Greek Empire, and owed as much to the mathematical heritage of the Egyptians as the Greeks. Alexandria became a hub of academic excellence under the rule of the Ptolemies in the 3rd century BC, and its famous library soon gained a reputation to rival Plato's Academy.
The kings of Alexandria were prepared to invest in the arts, in culture, in technology, mathematics, grammar, because patronage for cultural pursuits was one way of showing that you were a more prestigious ruler and had a better entitlement to greatness.
The old library and its precious contents were destroyed when the Muslims conquered Egypt in the 7th century. But its spirit is alive in a new building. Today, the library remains a place of discovery and scholarship.
Mathematicians and philosophers flocked to Alexandria, driven by their thirst for knowledge and the pursuit of excellence. The patrons of the library were the first professional scientists, individuals who were paid for their devotion to research. But of all those early pioneers, my hero is the enigmatic Greek mathematician Euclid.
We know very little about Euclid's life, but his greatest achievements were as a chronicler of mathematics. Around 300 BC, he wrote the most important textbook of all time, the Elements. In the Elements, we find the culmination of the mathematical revolution which had taken place in Greece. It's built on a series of mathematical assumptions called axioms. For example, a line can be drawn between any 2 points. From these axioms, logical deductions are made and mathematical theorems established. The Elements contains formulas for calculating the volumes of cones and cylinders, proofs about geometric series, perfect numbers and primes. The climax of the Elements is a proof that there are only 5 Platonic solids. For me, this last theorem captures the power of mathematics. It's one thing to build 5 symmetrical solids, quite another to come up with a watertight, logical argument for why there can't be a 6th. The Elements unfolds like a wonderful, logical mystery novel. But this is a story which transcends time. Scientific theories get knocked down from one generation to the next. But the theorems in the Elements are as true today as they were 2,000 years ago.
When you stop and think about it, it's really amazing that it's the same theorems that we teach. We may teach them in a slightly different way, or we may organize them differently, but it's Euclidean geometry that is still valid, and even in higher mathematics. When you go to higher dimensional spaces, you're still using Euclidean geometry.
Alexandria must have been an inspiring place for the ancient scholars, and Euclid's fame would have attracted even more eager young intellectuals to the Egyptian port. One mathematician who particularly enjoyed the intellectual environment in Alexandria was Archimedes.
He would become a mathematical visionary.
The best Greek mathematicians, they were always pushing the limits, pushing the envelope. So Archimedes did what he could with polygons, with solids. He then moved on to centers of gravity, or he then moved on to the spiral. This instinct to try and mathematize everything is something that I see as a legacy.
One of Archimedes' specialities was weapons of mass destruction. They were used against the Romans when they invaded his home of Syracuse in 212 BC. He also designed mirrors which harnessed the power of the sun to set the Roman ships on fire. But to Archimedes, these endeavours were mere amusements in geometry. He had loftier ambitions.
Archimedes was enraptured by pure mathematics and believed in studying mathematics for its own sake and not for the ignoble trade of engineering or the sordid quest for profit.
One of his finest investigations into pure mathematics was to produce formulas to calculate the areas of regular shapes.
Archimedes' method was to capture new shapes by using shapes he already understood. So, for example, to calculate the area of a circle, he would enclose it inside a triangle, and then by doubling the number of sides on the triangle, the enclosing shape would get closer and closer to the circle. Indeed, we sometimes call a circle a polygon with an infinite number of sides. But by estimating the area of the circle, Archimedes is in fact getting a value for pi, the most important number in mathematics.
However, it was calculating the volumes of solid objects where Archimedes excelled. He found a way to calculate the volume of a sphere by slicing it up and approximating each slice as a cylinder. He then added up the volumes of the slices to get an approximate value for the sphere. But his act of genius was to see what happens if you make the slices thinner and thinner. In the limit, the approximation becomes an exact calculation. But it was Archimedes' commitment to mathematics that will be his undoing.
Archimedes was contemplating a problem about circles traced in the sand when a Roman soldier accosted him. Archimedes was so engrossed in his problem that he insisted he'd be allowed to finish his theorem. But the Roman soldier was not interested in Archimedes' problem and killed him on the spot. Even in death, Archimedes' devotion to mathematics was unwavering.
By the middle of the 1st century BC, the Romans had tightened their grip on the old Greek Empire. They were less smitten with the beauty of mathematics and were more concerned with its practical applications. This pragmatic attitude signalled the beginning of the end for the great library of Alexandria. But one mathematician was determined to keep the legacy of the Greeks alive. Hypatia was exceptional, a female mathematician, and a pagan in the piously Christian Roman Empire.
Hypatia was very prestigious and very influential in her time. She was a teacher with a lot of students, a lot of followers. She was politically influential in Alexandria. So it's this combination of high knowledge and high prestige that may have made her a figure of hatred for the Christian mob.
One morning during Lent, Hypatia was dragged off her chariot by a zealous Christian mob and taken to a church. There she was tortured and brutally murdered. The dramatic circumstances of her life and death fascinated later generations. Sadly, her cult status eclipsed her mathematical achievements. She was in fact a brilliant teacher and theorist, and her death dealt a final blow to the Greek mathematical heritage of Alexandria.